Good morning, friends. In previous lecture, we
Good
have
morning.
discussed introduction of centrifugal pump. Today, we have discussed about efficiencies of centrifugal pump. In previous lecture, we have seen working construction of pump classifications and other types of the pump, impellers and casing like that. Means total construction and maneuver head, um, total head like that, friction head. So after that, we have discussed here, today's we have discussed here efficiencies. In case of centrifugal pump, the power is transmitted from the shaft to electric motor to the shaft of the pump and then to the impeller. From the impeller, the power is given to the water. The following are important efficiency of centrifugal pump: manometric efficiency, mechanical efficiency, and overall efficiency. So manometric efficiency here in this here three efficiencies we have discussed here: manometric efficiencies, after that mechanical efficiency and overall efficiency. So manometric efficiency of the pump, it is defines as the ratio of manometric head developed by the pump to the head imparted by the impeller to the liquid. So manometric efficiency equal to manometric head upon head imparted by impeller to the liquid. Okay. So manometric head we have denoted HM and head imparted by impeller to the liquid, it is VW to U2 upon G. So after rearrange our equation, so manometric efficiency equal to GHM upon VW to U2. G here gravitation, HM here manometric head, VW2 velocity of wheel at outlet, U2 outlet blade velocity. The power at the impeller of the pump is more than that the power given to the liquid at outlet of the pump. The power at the impeller of pump is more than the, the power given to the liquid at outlet of the pump. The power given to the water at outlet of the pump is WHM upon 1000, means rho GQ HM upon 1000 K. So power at the impeller, work done by the impeller per second upon 1000. So rho Q VW to U2 upon 1000 in kilowatt. So this is work done by impeller per second upon 1000. So power at impeller like that. So after that manometric efficiency, today we have discussed mechanical efficiency. So mechanical efficiency, it is defined as the ratio of the power actually delivered by the impeller to the power at the shaft of the centrifugal pump. Power at the impeller to power at the shaft means impeller power to shaft power. So impeller power means mass flow rate into VW to U2 upon 1000 and shaft power in kilowatt. So this is mechanical efficiency. After that, overall efficiency, it is defined ratio as the ratio of power output of the pump to the power input to the pump. So power output of the pump equal to weight of water lifted into HM upon 1000. So W into HM upon 1000 kilowatt. Power input to the pump equal to power supplied by the electric motor. So shaft power of the pump, so overall efficiency equal to WHM upon 1000 upon S into the shaft power. So overall efficiency equal to manometric efficiency and into mechanical efficiency. This is our overall efficiency. Now minimum starting speed when a pump is started, water will not flow until the pressure developed by the impeller is sufficient to overcome the manometric head, the water will start flowing only if the centrifugal head or pressure head rise by the impeller be at least equal to or more than manometric head. So centrifugal head or head rise by the impeller equal to U2 square upon twice G minus U1 square upon twice G. When see a minimum starting the minimum starting speed, when a pump is started, water will not flow until the pressure developed by the impeller is sufficient to overcome an manometric head. The water will start flowing only if the centrifugal head or pressure head rise by the impeller be at least equal to or more than manometric head. So centrifugal head or head rise by impeller equal to U2 square upon twice G minus U1 square upon twice G. This is head rise by the impeller. So where U1 is the tangential velocity of impeller at inlet and U2 is the tangential velocity of impeller at outlet. The flow of water commences only if U2 square twice G minus U1 square twice G or greater than or equal to manometric head. For minimum speed, U2 square upon twice G minus U1 square upon twice G equal to manometric head. So see, but manometric head equal to GHM upon manometric efficiency equal to GHM upon VW to U2. So HM equal to efficiency into VW to U2 upon G. This is equation for minimum speed, starting speed of the pump. So substitute the value of HM in equation, we get U2 square upon twice G minus U1 square upon twice G. So efficiency into VW to U2 upon G. So U1 equal to pi d1 n by 60 and U2 equal to pi d2 n by 60. So after rearranging and putting value of U1, U2, we are getting by dividing with pi n by 60g, we get pi n d2 square upon 120 minus pi n d1 square upon 120. So manometric equal to manometric efficiency into VW to d2. So pi n by 120 is common, d2 square minus d1 square equal to efficiency VW to d2. So n equal to 120 manometric efficiency VW to d2 upon pi into d2 square minus d1 square. Equation gives minimum starting speed of centrifugal pump. So see, in this derivation, we have find out minimum starting speed. So when the pump is started, water will not flow until the pressure developed by the impeller insufficient to overcome and manometric head. The water will start flowing only if the centrifugal head or pressure head rise by the impeller be at least equal to or more than manometric head. It is very important sentence. The water will start flowing only if the centrifugal head or pressure head raised by impeller be at least equal to or more than manometric head. So centrifugal head or head rise by the impeller U2 square twice G minus U1 square upon twice G, where U1 tangential velocity of impeller at inlet and U2 tangential velocity of impeller at outlet. The flow of water commences only if U2 square upon twice G minus U1 square upon twice G greater than or equal to HM. For minimum speed, U2 square upon twice G minus U1 square upon twice G equal to HM. But manometric efficiencies formula. So from this manometric efficiencies formula, find out HM. After find out HM, substitute the value of HM from equation 4.17. So after that, putting the value of U2 and U1 pi dn by 60, we are common out from this equation after putting common the pi n by 120, and after rearranging finding n, we are getting 120 into manometric efficiency into VW2 D2 upon pi D2 square minus D1 square. So equation gives minimum starting speed of centrifugal pump. This is for maximum suction rate of suction height, shows a centrifugal pump that lifts the liquid from some. The pre-surface of the liquid is the depth of Hs below the pump axis. The liquid is flowing with a velocity of Vs in the suction pipe. Figure 4.4 suction lift shows the centrifugal pump that lifts the liquid from a sump. The free surface of the liquid is at a depth of Hs below the pump axis. The liquid is flowing with a velocity of Vs in the suction pipe. So this is a show centrifugal pump that lifts liquid from the sump. The free surface of the liquid is a depth of Hs below the pump axis. Below the pump axis, the liquid is flowing with velocity of Vs in the suction pipe. So this is maximum suction rate. See here, Hs is the suction height of the suction pipe, suction rate. This is some pre-surface liquid suction pipe, section 1. Applying Bernoulli's equation at pre-surface of the liquid in sump and section 1 in the suction pipe just at inlet of the pump. Take pre-surface of liquid as a bottom line, we get PA upon rho g plus VA square upon twice g plus ZA. P1 upon rho g plus V1 square upon twice g plus Z1 plus HL. Atmospheric pressure of the pre-surface of the liquid. Velocity of liquid at the pre-surface. Height of pre-surface from bottom line. Absolute pressure at inlet of the pump. Absolute pressure at inlet of the pump, velocity of liquid through suction pipe V2, Vs, height of inlet pump from bottom line Hs, loss of head input wall, strainer and suction pipe HFS. So PA upon rho g plus 0 plus 0, P1 upon rho g means we are putting these values, total values, P1 upon rho g plus Vs square upon twice g Hs plus HFS. So, see here, one minute. So, see here, PA upon rho g means atmospheric pressure head. Atmospheric pressure head upon rho g equal to P1 upon rho g and Vs square upon twice g plus Hs plus HFS. P1 is the absolute pressure at inlet of the pump. So this is P1 upon rho g equal to PA upon rho g minus Vs square upon twice g plus Hs plus HFS. For finding maximum suction, for finding maximum suction pressure at the inlet of the pump should not be less than vapor pressure of the liquid. He is taking minimum pressure at inlet of the pump equal to vapor pressure of the liquid. So we get P1 equal to PV, where vapor pressure of liquid is absolute vapor pressure of liquid is absolute unit. So PV upon rho g equal to PA upon rho g minus VS square upon tau g plus HS plus HFS. So HS equal to PA upon rho g minus PV upon rho g minus VS square upon tau g minus HFS. So PA upon rho g equal to HA atmospheric pressure head. PV upon rho g equal to HV the vapor pressure head. So HS equal to HA minus HV Vs square upon tau g minus HFS. So equation 4.20 gives value of maximum suction rate for centrifugal pump. Hence, if the suction height of the pump is more, then the vaporization of a liquid at the pump inlet of pump will take place and there will be a possibility of cavitation. So net positive suction head, it is defined as the total head developed at the pump inlet above the vapor pressure of the liquid. So it is also defined as the absolute pressure head at inlet of to the pump minus the vapor pressure head plus the velocity head. Thus, NPSH P1 by rho g minus PV by rho g plus Vs square upon tau g. Introducing the value of P1 by rho g from equation 4.19, in the above expression we get NPSH PA by rho g minus Vs square upon tau g plus SH plus HFS minus PV upon rho g plus Vs square upon tau g. So net positive suction head PA by rho g minus PV by rho g minus HS suction head and minus frictional suction head. So NPS is equal to HA minus suction head minus frictional head minus HV head of pressure. In other words, PNPSS may also be defined as the total head required to make the liquid to flow through suction pipe to the impeller. For any pump installed, a distinction is made between the required NPSS and available NPSS. It is defined as the total head developed at the pump inlet above the vapor pressure of liquid. It is also defined as the absolute pressure head at the inlet to the pump minus the vapor pressure head plus the velocity head. So NPSS equal to P1 by rho g minus PV by rho g plus Vs square upon tau. So after final equation we are getting NPSS rearranging equation. We are getting NPSS equal to HA minus HS minus HFS minus HV. For any pump installation or distinction is made between the required NPSH and the available NPSH. Required NPSH, the value of required NPSH is given by the pump manufacturer. The value of required NPSH varies with the pump design, the speed of the pump, and the capacity of the pump. The value of required NPSH can be calculated experimentally for determining its value, and the pump is tested with different suction reps, and minimum value of HS is obtained at which pump give maximum efficiency without any objection or noise. So cavitation free, here this is required in net positive suction head. The value of required net positive suction head is given by the pump manufacturer. The value of required NPSH varies with the pump design. speed of the pump, and the capacity of the pump. The value of required NPSH can be calculated by experimentally. For determine its value, the pump is tested with different suction rate and minimum value of HS is obtained at which the pump gives maximum efficiency without any objectionable noise. Available NPSH. When the pump is installed, the available NPSH can be determined from the equation. In order to have cavitation-free operation of centrifugal pump, the available NPSH should be greater than the required NPSH. When the pump is installed, the available NPSH can be determined from the equation. In order to have cavitation-free operation of centrifugal pump, the available NPSH should be greater than required NPSH. NPSH net positive suction head, the NPSH curve not pumping so hard to avoid cavitation in centrifugal pump. To avoid cavitation in centrifugal pump, the pressure of the fluid at all points within the pump must remain above saturation pressure. To avoid cavitation in centrifugal pump, the pressure of the fluid at all points within the pump must remain above saturation pressure. The quantity used to determine if the pressure of the liquid being pumped is adequate to avoid cavitation is the net positive suction head. The quantity used to determine if the pressure of the liquid being pumped is adequate to avoid cavitation is the net positive suction head. Divided into two parts, net positive suction head available and net positive suction head required. So net positive suction head available, the absolute pressure at the suction port of the pump, the absolute dynamic head of the pump inlet in exceed of the vapor pressure. NPSS curve not pumping so hard to avoid cavitation in centrifugal pump. The pressure of the fluid at all points within the pump must remain above saturation pressure. The quantity used to determine if the pressure of the liquid is being pumped inadequate to avoid cavitation is the net positive suction head. Divided into two parts, NPSS available and NPSS required. So NPSS available, the absolute pressure at the suction port of the pump, the absolute pressure at the suction port of the pump, the absolute dynamic head at the pump inlet in exceed of the vapor pressure. So see here, NPSH, net positive suction head, equal to HA minus HV plus HS plus HVS plus HFS. So HV is a pressure head and HS is a suction head, HVS velocity head suction, and HFS frictional loss in suction pipe. So NPSH A greater than NPSH R to avoid cavitation, it's the positive pressure required at the pump inlet. Need to compare available to required NPSH. NPSH required, the minimum pressure required at the suction port of the pump to keep the pump free from cavitating. The minimum value of NPSHA that is need to prevent cavitation in the pump, that is the value of NPSH that causes P minimum to equal P vapor. So NPSHR is determined experimentally by pump manufacturers and recorded as a function of pump flow rate. To avoid cavitation, always operate with NPSHA greater than NPSHR. NPSH required means the minimum pressure required at the suction port of the pump to keep the pump free from cavitation. For that, we have used NPSH. After that, the minimum value of NPSH NPSH, however, that is need to prevent cavitation in the pump. That is value of NPSH, however, that causes P minimum to equal to P vapor. So NPSH required is determined experimentally by pump manufacturer and reported as a function of pump flow rate. To avoid cavitation, always operate with NPSHA and NPSHR. So net positive suction head required, the pump manufacturer specified margin of the suction pressure above the boiling point of the liquid being pumped is required to prevent cavitation. This pressure is called the net positive suction head pressure. In order to ensure that NPSH pressure is maintained, the available NPSH should be higher than required. The NPSH depend on the height and density of the liquid and the pressure above it. The net positive suction head required. The pump manufacturer specified margin of the suction pressure above the boiling point of the liquid being pumped is required to prevent cavitation. This pressure is called the net positive suction head pressure. In order to ensure that NPSH pressure is maintained, the available NPSH should be higher than required. The NPSH depends on the height and density of a liquid and the pressure above it. Specific speed. The specific speed of centrifugal pump is defined as the speed of geometrical similar pump which deliver unit quantity against unit head. So up to C, we have seen NPSH and all parameters here. See, this is, we have seen efficiency. After that, in this mechanical efficiencies, after that overall efficiencies, after that minimum starting speed required for the pump, we have find out this pump speed. Now maximum suction grip of suction height, we have find out VHHS. Take free surface liquid as per Dotomrine applying Bernoulli's equations for Dotomrine and find out all parameters and velocity of liquid at free surface, it is 0, and height of free surface, it is also 0 from Dotomrine. So put the value of 0 and we are getting and rearrange the equation. So see here, is taking minimum pressure at inlet of the pump equal to vapor pressure of the liquid P1 equal to PV. So vapor pressure of the liquid is absolute unit. Can I say vapor pressure equal to of the liquid is absolute unit? So PV upon rho G equal to PA upon rho G minus Vs square upon twice G plus Hs plus HFS. So after HS suction head we are getting equal to atmospheric head minus atmospheric vapor pressure. So yeah, vapor pressure, VHV is the vapor pressure head, PV upon rho G. So V1, V2 square upon rho G, HF2. So equation 4.20 gives value of maximum suction rate for a centrifugal pump. Hence the suction height of the pump is more than the vaporization of liquid at the inlet of the pump will take place, and there will be possibility of cavitation. If the suction height of the pump is more, then vaporization of liquid at height at the inlet of the pump will take place, and there will be possibility of cavitation. This condition is applied for cavitation. After that, NPSH with positive suction head, it is defined as the total head developed at the pump inlet above the vapor pressure of liquid. So MPSH calculated by HA minus HS minus FS minus HV. After that, NPSH installation distinction is made between the required NPSH and available NPSH. This is NPSH required and NPSH positive suction is required. After that, we have to discuss here specific speed now, but today we have stop here, and this is discussed in next lecture. So any doubt, any queries, please ask me on WhatsApp and our videos. So any doubt, any queries in today's lecture, please ask me. Okay, no doubt. So next lecture is the last lecture for theoretical part of the 5th unit centrifugal pump. After that, we have solved the problem of the centrifugal pump. So all of you requested to attend these lectures because VIMP lectures gone for centrifugal pump. So any doubt, any queries, please ask me. Okay. So we have considered no doubt, no queries. So today we have stopped here. Thank you. Today I am sharing attendance link. Marks your attendance on this link. So thank you.